My name is Zhao Zichen. I'm a PhD student from Department of Mathematics, National University of Singapore. Today, I will present our work, Adaptive Sampling Method for Learning Dynamics. This is a joint work with Professor Chen Xiaoli. Here is the outline for my today's talk. In the first part, I will quickly review some current learning methods and introduce the background and motivation of adaptive sampling. In the second part, I will give mathematical formulations of learning dynamics and discuss the difference with classical supervised learnings. And next, I will present the adaptive sampling algorithm and the numerical result. So, modeling dynamical systems based on observed trajectory data is an important course in numerous domains of science and engineering. With growing data availabilities and computational powers, data-driven methods have become a promising alternative to traditional modeling techniques for studying dynamical systems. Recently, there are many works on this field, such as SND, DIN, PDNet, and quasi-potential computational, and so on. So the core problem of our work is how to improve the sampling efficiencies for learning dynamics. Here is the basic workflows for learning dynamics. In the step one is samplings. We already have some simulators for the underlying dynamics. So what we need to do is collect data from n trajectories with density. Then the second step is learnings. We need to select some underlying models and minimize the empirical risk over the sampled data. And the last step is evaluations. We need to calculate the target risk to quantify the behavior of learned systems. So in classic supervised learning, we just need to calculate the generalization error, right? But in the dynamical setting, the target risk can be quite different. I will explain this later. In fact, most previous work focused on the second step. The learning steps try to develop in some new network architectures or training methods to learn. So here I will quickly review 3 learning methods. The first one is sparse regression or sparse regression identity of linear dynamics using some predefined function dictionaries. The second method called PIN, physical informed neural network, using the PDE regulations to learn the underlying physical laws. And the last one is data-driven quasi-potential using both field decomposition. Roughly speaking, the red hat and F can be decomposed into 2 terms, which satisfy the orthogonal conditions. So besides the step 1 in the workflow, the sampling step and the evaluation step are also important. Actually, there is a chicken and egg problem during sampling and the learnings. On the one hand, a correct model is also a prerequisite for an efficiently sampling strategy. On the other hand, properly sampled data is indispensable for learning and accurate models. Next, I will give 2 examples to explain the chicken and egg problem. So the first example is the systems with double well potentials. The most important point here is the saddle point. So if you want to modeling the dynamics around saddle point, you need to control the trajectories across the saddle point, right? But if we have knowledge about the location of saddle point, one cannot do such things. And similar phenomena can be found in the dynamic systems with attractors. For example, for the systems with uniform linear cycles, if one use short trajectory to sample to do samplings, then the trajectory may not long enough to cover the invariant measure. If one use a very long trajectory to do, then he may cover the same information many times, which cause a waste and decrease the sampling efficiency. So we need adaptive algorithms that combine the step 1 and step 3 to do sampling. Next, I will give the mathematical formulations of learning dynamics. So here we consider the discrete time dynamical systems xt plus 1 equal to f star fst. Our goal here is to recover the target function f star. And step 1, the sampling data is collected from n trajectories with length t and is partitioned as input-output pairs in these forms. And then we can define the empirical measures mu nt, which is the discrete distributions over the sample data. And next, the second step learning. So we build up some hypothesis space H. Here we only have one assumption that all the function in H is ellipsis functions. And then we learn an approximation f star by solving the empirical risk minimization. Well, the empirical risk LNT is in this form. So it's just so one step for a loss function over the empirical distributions. Here D is the loss functions. We need D to be a symmetric satisfy the row triangular inequalities, because we want to cover the most popular choice mean square errors. And for other applications, it can be a matrix. For example, the L1 regressions. And next, we come to the last step evaluations. Here, we define the target risk L star theta as the model performance. So L star theta in these forms is one step push forward over the measure mu star. So the target measures here can be taken variable forms depending on applications. In the classical supervised learning, the target risk L star is just the expedition of the empirical errors. So because the training data is just IID select from some distribution mu0, right? But in the dynamical situation, there are two main differences. First, multiple performance metrics can be chosen according to different practical goals. Secondly, they involve performance metrics that are associated with necessarily different distribution from the empirical distribution. Next, I will give some examples about the applications. So the first one is here. Our goal is to recover the right-hand side vector field f star over some domain of interest f. Then the target measure mu star can be selected as the corresponding uniform distribution. And the target risk can be expressed in these forms. That's the MSE errors over the uniform distribution of S. And in example 2, the goal is to approximate the vector field f star over the invariant measure. So in this case, mu star should be taken as the invariant distribution of the dynamics, right? And then the target risk can be expressed in this form. And when we come to the example 3, actually one important case that cannot be covered by our previous definition of L star is the multi-stacked prediction, right? So in this case, the multi-stacked target risk L star can be expressed this way, right? But once we select some proper mu star, we can also control the multi-step target risk by the previous risk form. Here the k-hat is the uniform Lipschitz constant of all hypotheses in the hypothesis space H. So next we have a brief summary. So the target risk L star, which is dependent on the choice of mu star, can be seen as the general formulation of the performance indicators, right? And the sample A measures mu nt does not in general converge to the target measure mu star as n or t goes to infinite. This is quite different from the classical supervised learnings. So balancing sampling cost and the model performance is quite important. Actually, we can say we want to control the sampling measures mu nt close to the target measure mu star. In the next section, I will show that the model performance can be bounded by the distance between mu nt and mu star. So next, so first we give the Washington distance definitions between two probability measures. And we have the following dual representation. So in the next slide, we have the main propositions of our work. The upper boundary of target risk, which it says that the target risk with respect to U star can be bounded by assumption of three parts. The first part is model bias. Second term is empirical error, and the last term is less than one distance between sampling and the target measure. Moreover, if the hypothesis space is a uniform, if H is the uniform approximators, which means the model bias can be reduced to zero, this term just vanished. And if we can get theta hat as the empirical risk minimizers, then the empirical error can also be reduced to zero. So the target risk, then we just have this upper boundary for just target risk, which is then the target risk is only bounded by the constant distance between mu star and mu nt. So once we have these propositions, one can design sampling strategies that minimize the one Washington distance between sampling and the target measure to reduce the target risk. So there are two important parameters: the number of starting points n and the trajectory length t. Because one can always IID draw the initial endpoint from some initial distribution. So in this work, we only focus on how to select the second parameter. Given the initial point, how to find the appropriate trajectory length to samples. So once the target measure mu star is selected according to our applications, we can formulate the sampling problem of finding optimal T as an optimization problem that minimizes the one Washington distance with the cost term phi. So this is our optimization problems subject to the underlying measure transformations. So here we take the limit cycles as the toy models to demonstrate that the R-bundle target risk and the optimization formulation are sensible. So in the left fingers, we have two curves. The red curve represents the Washington distance, is the Washington distance well the trajectory length, while the blue one is target risk calculated with different with different sampled data collected from the trajectory length input as input. And from this figure, we can see these two curves, the trend of two curves match very well. And after this point, the disagreement of both both curves seems insignificant. So, which means we can use the Gaussian distance decreasement to control the target risk. And in the right figure, the only difference is that the green one is the only difference between the green one and the red one is that the green one is added with the cost terms. So based on the main propositions, we have the basic algorithms. So we just unfloat the dynamics and calculate the decreasement of the Gaussian time distance. Then if the Gaussian distance do not decrease significantly, we can stop sampling and generate the output data. So here are some details of algorithm 1. The stop quarantine is selected as the relative error, which is the combination of the Gaussian distance and the cost terms. And here's cost term can be naturally taken as the linear forms. Since the natural assumption is that the sampling cost is a proportion to the number of data points and the time horizon. And to calculate the Gaussian distance, we select M points that I draw from the continuous distribution mu star to construct the discretization of the target measures, and then using Zichen algorithm to calculate the optimal transport problems between two discrete data sets. And here we have the first variant of the basic algorithms. So we can recall the chicken egg problems. In some cases, the target distribution mu star is inaccessible. For example, the invariant measures So, which means one cannot cheaply draw samples from the mu star. In this case, we need to first generate a temporal simulator f hat as solving the empirical risk minimizations over the current sample data. Then we can, once we have the cheaper simulators, we can generate the trajectories and approximate the samples from mu star without any cost. Once we have the discretization of mu star and the simulators, we can substitute them into the basic algorithms. So here is algorithm 2. The only difference is highlighted by blues. And here we also take the limit cycle learning as examples. So in this case, the target risk is selected as the inaccessible invariant distribution. So we cannot directly draw samples from the unit cycles. But using the algorithm tool, we can say we can adapt it. We can gradually capture the unit cycle, and the target risk decreased significantly. Right? And the second variant is adaptive trajectory-wise case. So for sampling problems, it's one initial measures, one trajectory length here as the output is enough. But in practical, for the starting point n larger than 1, there is usually no uniform trajectory length, right? So in this case, we can modify the original optimal problems, and the original one is only over 1T Commonwealth, but in this case, we can modify it over the all initial points. So we got T1 and Tn. Actually, this optimal problem is very hard to directly solve. But we observe that if a trajectory overlapped with one another, then the extension of the trajectory contributes less to the decreasing of one than one distance, because the overlapped one is already collected by some previous trajectory. So based on this observation, we propose algorithms including overlapping checks to approximately solve the optimization problem. So in this case, we have three different starting points, and we apply both algorithm 1 and algorithm 3. The left graph is output of algorithm 1 with common trajectory, right? And so you can see there are some overlappings between the original and the blue ones. And in the right fingers, it's sampling result of algorithm 3. There is no overlappings, and we can check the sampling budget. The budget of algorithm 3 is 85, while the budget of algorithm 1 is 105. So there is 20% sampling reduction. So the only difference between algorithm 3 and algorithm 1 is that we add overlapping check step here. Finally, we also have algorithm 4, which combines both inaccessible target measure and adaptive trajectory wise. And we summarize all 4 algorithms in this table. Next, we will show some numerical results. So first, we want to show our sampling method can be adaptive to different types of dynamical systems. So the first case is dynamical learning problem of Lorentz 16 series. The setting is that the mu star is inaccessible. It's multi-stepped trajectory prediction errors. And our goal is to model the dynamics from one long trajectories. So here we applied algorithm 2 here. And we can see our algorithm can gradually capture the limit cycles, and the target risk decreased via the iterations. And in the second case, we try to recover the right-hand side vector field in bistable systems. So algorithm 3 is applied here, and the target measure mu star is selected as the uniform distribution over the region of interest S. And we can see since the trajectory converge much faster to the left stable state, so the trajectory stop earlier for this for this 4. And the last example is on-damper accelerators. Our goal is to model the dynamics over its inaccessible limit cycles. In this case, the target risk L star can be taken in these forms. So algorithm 4 is applied here to learn the fundamental accelerators. We have 3 different initial points, and we can say the algorithm can capture the limit cycle gradually. And in the previous 3 examples, we use 3 fully connected neural networks to train models. So here we also apply we also change the learning method, use the random filter models with Gaussian kernel to do the same things, and compare the results from adaptive samplers to the baseline passive samplings. So this table shows a target risk with fixed budget, with fixed sampling budget NT. And we can see our adaptive sampler outperforms the baseline. And in the table 4, we show the result of recurrent data point with fixed error tolerance. Similarly, we also applied 2 learning methods here, and we can see our active samplers require less data compared to the baseline passive sampling method. Next, we want to show that our method can be efficiently combined with existing learning method. So here we consider the dynamics with some quasi-potentials. And algorithm 3 is applied here to recover the right-hand side vector field. And the learning method is selected as the data-driven quasi-potential method, which I introduced before using the vector field decomposition. So in this case, since the network is very complicated, we need many data as input. So here, the initial starting point n is selected as 100, and we use a subsampling strategies for the large n. So we divided the n into 15 groups, and each time we apply the algorithm 3 for two trajectories. And we can say our budget is much smaller than the baseline sampling one. Okay, finally, I will do a quick conclusions. So, our adaptive sampling method is motivated by the gaps between evaluations of model performance and sampling strategy. And the evaluation of the performance varies with different applications. And we bring up 4 different adaptive algorithms with regard to the accessibilities of the target measures and trajectory-wise adaptivity. And through the numerical results, we show that our method are adapting to different types of dynamic systems, outperforming baseline method, and can be efficiently combined with existing learning models.